Hey everyone, and welcome back to Learning with Jelly. So today is the first video for our Statistics in Python series. I'm very excited for this series. It is recommended by tons of students, and statistical concepts are asked a lot in technical interviews if you're going into a data career. Now, in order to follow along, I'm going to have a link to the GitHub repo in the description below, where within the statistics folder, you're going to be able to find this notebook so that you can practice and follow along with me. We're going to talk about three distribution functions today: the probability mass function known as PMF, the probability density function known as PDF, and the cumulative density function known as CDF. Okay. And the main difference between the PMF versus the PDF and CDF is going to be the type of numeric variable you have. So if you have a discrete numeric variable, which we're going to talk about, you're going to utilize the PMF. And anything that's continuous and numeric, we're going to utilize the CDF. So some objectives for this presentation, we're going to talk about distributions and why are they important in data careers, especially for data analysts and data scientists. We're going to define that probability distribution. We're going to look at several types of probability distributions. We're going to talk about the probability mass function, and we're going to be able to run an example in Python. And we're also going to talk about the relationship between the PDF and the CDF. So to get started, why should you care about distributions to begin with? So the distributions of your data can determine what analytics you perform and what model you utilize. Okay. So how your data is distributed can determine what predictive model you're going to utilize. So an example of different business questions that have different forms of distribution could be predicting the number of car crashes during a specific time period. Because it has a specific time period, that is a Poisson distribution. Predicting water pump failure, so either it fails or it doesn't fail. So since that's a binary outcome, that is an example of a Bernoulli or binomial distribution. And then predicting the birth weight of a baby is a normal distribution. So there's tons of business use cases based off of your business use case and the underlying data that is going to impact what type of model and or what type of analytics you perform, such as how you are going to deal with missing values. Okay, so let's hop right into the definition of what a probability distribution is. So it's a stats function of all the possible values and likelihoods that a random variable can take. Okay, so I have this random variable. What is the likelihood of this random variable? So a random variable can be any discrete or continuous numeric variable. Discrete meaning that it's a number and it has defined categories. So something like number of eggs in a basket. If we do a coin flip, right, that can be coded as 1 for heads, 0 for tails. If we're looking at a dice, I can have a category of 1 through 6. Okay, so it's a discrete numeric variable. Something that is continuous has a range of values like my height, like my weight, like standardized test scores, BMI, things of that nature. Okay. So we have tons of probability distributions, okay? So we have a uniformed, Bernoulli, and binomial, and you're going to see examples of those three today. We also have one of the most popular ones, which is normal or Gaussian distribution, and we're going to look at that today as well. But there are also other probability distributions that you may encounter within your data career. I highly recommend, if you're trying to grasp on to statistics concepts, it's always good to make your own cheat sheet or a chart of defining characteristics with distributions. So in this case, I have 5 distributions listed out, and the normal distributions is defining characteristic is this distinctive bell shape. And we're going to talk about that bell shape momentarily and also in the next video. And one of its applications is when I'm using least squares fitting. So that's going to be for linear regression. Okay. I also, for instance, have the binomial distribution, and that's when I have 2 outcomes. So a head versus a tail, a car being a lemon and not a lemon, a water pump failing and not failing. And this is going to be used anywhere there's a binary outcome. Yes, no, black, white, didn't vote, did vote. Okay. So try to make yourself a little cheat sheet to kind of keep all of these distributions together about what are some of the defining characteristics of these distributions and what are the applications behind it, right? And sometimes visuals help to look at some of these defining characteristics. So for instance, for Bernoulli, I see that I just have two bars. One is going to be 0 outcome. The other one is going to be an outcome of 1. And I see that the Bernoulli is related to binomial. I see that the uniform, all of my bar heights are the same. So the probability of any event is going to be the same across my data. Okay, so look at some defining characteristics and also get to know the application. So we're going to talk about the Bernoulli, which we already know is going to have an outcome of 0, 1, or a binary outcome. And then we're going to talk about its child, which is binomial. Okay, so the Bernoulli distribution is a type of probability mass function because it's going to utilize a discrete numeric variable. So that mass denotes discrete numeric variable. So anytime you have a discrete numeric variable, like number of eggs in the basket, a coin toss, winning or losing a game, the car being a lemon or not being a lemon, a water pump malfunctioning or functioning, it has pretty much a success and a failure outcome, aka a binary outcome. We're going to utilize probability mass functions, right, for discrete variables. So Bernoulli distribution, in this case, is going to be a discrete variable that's binary. So I give some examples here: tossing a fair coin, washing a single load of clothes to see if the articles shrink or not. So in my graph below, I have my successes denoted by 1 with that corresponding probability on the y-axis. So that means my failure is just going to be 1 minus the probability of my successes, right? Because both of these are going to add up to 1. Awesome. So outside of just having a single trial of an outcome, I can have multiple trials. And this is where the binomial distribution comes into play. So it's still going to utilize a discrete numeric variable. So we're going to use the probability mass function, but it's going to be pretty much a whole bunch of Bernoulli smashed together. Okay, so many different trials. So washing 10 loads of laundries and getting the probability of shrinkage for each load, the probability of winning or losing a season of games, tossing a coin 30 times for 20 trials, okay? And we're actually going to see an example of this last bullet point where we're going to be able to toss a coin X amount of times for X amount of trials, okay? So to keep up with these two, I love this visual here where we have the Bernoulli distribution just being one trial and the binomial distribution being multiple trials. Okay. The normal distribution is a probability density function. So anytime, or technically it's a cumulative density function, so we should change that to CDF. But anytime when you see density, think of a continuous variable, okay? So the normal distribution is widely utilized in data science, okay? So much so that we're gonna talk about it when we talk about in our next video. So a continuous numeric variable, something like height, something like weight, something like standardized test scores. It's going to be symmetric about the mean, where the mean is going to be the same as the median, which is the same as the mode. The area under the curve is going to equal 1. Okay. And it can be standardized. And we're going to talk about standardization in the next video. So pretty much, I have a bell curve. That's a characteristic of a normal distribution. At the center of the bell curve, there's going to be the mean. So if this was height, this would be, let's say, 76 centimeters. Okay, and I should be able to look underneath this curve to find probabilities at a certain point that is greater than that point or less than that point. Okay, and we're going to see an example of that momentarily. So this is a density function because it's utilizing a continuous numeric variable. Mass functions are going to utilize discrete numeric variables. So let's go back to the mass function and let's actually create our own binomial distribution. Keep in mind that binomial distributions have a binary outcome. So we're going to use a coin toss where heads is 1 and tails is 0. And before we go into making a binomial distribution, let's talk real quick about what a uniform distribution looks like. So probability mass function is going to be dealing with discrete variables. So if I have a die, right, and a die is 6 sides, so I can't roll a 2.3 on a dice. Okay, so that means that they are discrete. They have 6 categories if you want to look at it that way. The probability that I roll a 1 is 1/6. The probability that I roll a 2 is also 1/6. The probability that I roll a 3 is also 1/6, etc. So anytime where your discrete category has an equal probability of existing or happening, that is what we call a uniform distribution, right? And we saw what that looks like in the beginning of the lesson when we saw the different types of probability distributions, okay? So probability mass function, the probability for a value for a discrete random variable. An example of a uniform distribution, which is a type of probability mass function, is when we roll a die, okay? And we get equal probabilities of landing on each individual number. Okay, so now let's go ahead and run a binomial distribution in Python. So here we have SciPy stats, and we're importing the binom, okay? And I'm going to have some variables that I'm going to initialize, and then I'm going to use the binom.rvs function. RVS is just random variates, okay? So in order for my binomial distribution to be plotted out, I need to have the number of flips in this case, since I'm using a coin for each trial. I need to define the probability of success. So in this case, I know with a fair coin that it has a 50% chance on landing on heads. And I have to tell it how many trials I want to do. So I want to flip the coin 20 times for 25 trials. Okay. And so once I define these, I can run it into my binom.rvs function, okay, where I take in the number of flips, the probability of success, and how many trials I want to do. So when we run this, we get an array out, okay, and within this array, we see that I have 25 numbers. So 10 through 9 is 25 because that's how many trials I wanted. It also tells me how many successes out of the 20 flips do I have for each trial. So in this case, I had 10 heads out of 20 in my first trial. I had 9 heads out of 20 in my second trial. I had 9 heads or 9 successes out of 20 in my third trial. Okay? And then we're going to be able to plot that. So in this example, we've already utilized matplotlib in our Python for Fundamentals series. So go back and look at that if you need to. But I'm going to pass in the data underscore binom, which I generated here, which is an array of these values of successes. And then I'm going to print out that histogram, right? Where I have the number of successes, right, on the x-axis, and how many trials that appeared on the y-axis. So in this example, for instance, I need to figure out how many trials had 9 heads being flipped. And it tells me 5. So in my array up at the top, I should see 5 9s. So I have 1, 2, 3, 4, 5, right? So that ties out. How many trials did I have 12 heads or 12 successes? It said that I had it in one trial. So up in my array, I should only see 112. Okay. So that is how you can plot a binomial distribution. You have seen examples of this type of distribution within your data, whether you noticed it or didn't, but this can pop up in data as well. So coming from our Python from Fundamentals series, we're going to read in the same data set, which is our King County data set. Okay. From there, we are going to go ahead and look at the head of the data set, which is the first 5 rows, calling the dot head method. And I see that I have some numeric discrete variables, such as bedrooms in this case, such as condition, such as floors, such as grade. Okay, so I have some categories of numeric variables that exist within this data set. And then I'm going to do a quick value counts on one of those variables. Okay, so I'm calling the data frame in brackets. I'm passing the column name in quotes that I want to look at. And I'm going to get how many observations at each level are within each grade. So I see here that I have about 9,000 homes that are a grade of 7. I have about 6,000 that's a grade of 8. And so this is telling me how many observations, right, corresponds to each category of grade. I can then plot that out, and this is what I get, right? And I see that it ties up because a grade of 7 had about 9,000 homes with grade of 7, and that ties up to my value counts that I have up here. So very similar to what we have with the binomial distribution. Instead of the binomial distribution tells us how many trials had this number of successes. In this case, it tells me how many observations has this level of numeric variable. Okay, so slightly different, but the distribution looks pretty identical. Okay, so let's talk about the probability density function along with the cumulative density function all at once. Okay, so with the probability density function, all right, it wants to take the probability of a continuous random variable will take a value exactly equal to X. Okay, so I want to know what is the probability of that continuous variable right at that specific point. So if I have a bell curve, right, and say for instance, right here on my curve was 81, I want the probability of someone being of height 81. But since the probability is denoted by the area underneath the curve, the probability at any single point is going to be 0, right? So the probability at a height of 81 is 0. The probability at the height of 60 is 0 because it's one single point. So I can't calculate the area underneath that curve. And so because I can't calculate the probability at a certain point, I look around it. And looking around the point is how we derive the cumulative density function. So in essence, the probability density function is the derivative of the cumulative density function. And what the cumulative density function does is say, hey, I can't get the probability at 81 centimeters, but I can get the probability of less than or equal to 81. Right? And that area under the curve can be calculated and it's going to have a value that's different than 0. Okay, so let's look at the cumulative density function, which is going to be utilized quite a lot. And let's see an example. So in this case, and we did have an example of a standard normal distribution, but we're going to take that out. I'm going to import stats from scipy.stats. The value that I have in question is 80 centimeters. So I want to know, what is the probability that someone will have a height of 80 centimeters or less? Okay. And so with that being said, let me just remove this one comment because we're not doing standard normal right now. I'm going to do stats.norm.cdf, where I take in the value in question, which is 80 centimeters. Say, for instance, I know that the mean height is 76 centimeters and that the standard deviation is 2.5 centimeters. And so when I print this out, the probability of attaining a value less than or equal to 80 centimeters is about 95%. So 95% of this population is going to be 80 centimeters or less. Okay, and I can get that with the stats.norm.cdf function in Python. What if I wanted to, let's go ahead and retype that, stats.norm.cdf. What if I wanted to get the probability of being greater than my x, right? So I'm still going to use the stats.norm.cdf where I'm going to have my value in question, my mean, and my standard deviation. But in this case, I'm going to do 1 minus, okay? And so when I run this, I get the probability of being greater than 80 centimeters at about 5%. And both of these numbers is going to add up to 1. Okay, so I can't get the probability at exactly 80 because the area underneath the curve at exactly a single point is 0. But I can get the probability around that point. So I can get what's the probability of obtaining a value less than 80 centimeters or equal to, which is 95%. And I can get the probability of being greater than 80 centimeters at 5%. Okay, so we also can go back to the data set. And so I'm interested in the probability of a home in my data set that is less than or equal to 2,200 square feet of living space. Okay, so I can do a dot describe, and this is going back to our fundamental series. So check that out. This is in the pandas video. And I see that square foot living has a mean of about 2,080 square feet with a standard deviation of 918. Okay, so I have that information. And so now I can go ahead and run my CDF, right? Where I have the value in question, which is 2,200 square feet. I have the mean, and let's say that this mean is 280. So let's go ahead and do that. And I have the standard deviation, which is 918. And when I do that, I see the probability of having a home in my data set that's less than or equal to 2,200 square feet is 55%. Okay, so that's how I can utilize very quickly a data set to get its probabilities. Okay, and this is for continuous numeric variables when I use this density function. Okay. All right, so I hope that was a great overview of PMF, PDF, CDF. Please like, comment, and subscribe to stay tuned for the next stats video. And I will see you all then. Bye-bye.